A man pushing a mop across the floor causes it to undergo two displacements. The first has a magnitude of 150 centimeters and makes an angle of 120 degrees with the positive x-axis. The resultant displacement has a magnitude of 140 centimeters and is directed at an angle of 35 degrees to the positive x-axis. Find the magnitude and direction of the second displacement. So the very first thing I did was I drew a diagram. Pause. And so in essence, let's start with the first displacement vector. So first displacement vector, 120 degrees with the x-axis, 30 degrees with the y-axis if you use trigonometry, and that's the first displacement vector. The second displacement vector is actually not given to us. That's what we're solving for. So I drew just two parallel versions here, one for the triangle kind of ideal setting, but also just to showcase at what angle it is going to be coming at in this second scenario. And then finally, this is the resultant vector. So this comes from the combination of vector x1 and position vector x1 and position vector x2. So this is the culmination, and that can be seen in this triangle here. It's at an angle of 35 degrees, and theta represents the angle at which x2 is intersecting the x-axis. So, what did I do in terms of math? I first used something called a unit vector. For those of you who have not taken calculus yet, basically a unit vector is a simple way of mapping how you're going to be calculating your vector. So in this case, for u1, meaning the vector 1, for the position vector, first position vector, I used negative sine 30 degrees, cosine 30 degrees. So the sine 30 degrees comes from, if you can see it right here, there's an imaginary triangle here perpendicular to the y-axis. Sine 30 degrees would be the x component of this x1, of this first position vector. Another way you can look at it is if you just drew a line down here and then using trigonometry again, it would work. Now you're probably wondering, what does this negative mean? Well, because I set my conditions here for what is positive, this first position vector is actually moving in the negative x direction. It's moving this way. So I add a negative there in my unit vector. The second component is the y component. And again, if we imagine that triangle here, cosine 30 degrees would be the y component of the first position vector, and that is positive. So now I did a unit vector for the resultant vector, which is this one here. And so this time the x component is cosine 35 degrees. So if you can imagine, again, this is a unit vector. This is not using the hypotenuse or anything. This is just a way of setting up what is going to happen next. So cosine 35 degrees represents, the cosine 35 degrees, it represents the x component. Sine 35 degrees, y component. Enough said. So now what you do is, since this is now your vector here, you're going to multiply it by the values they give you. In this case, they give you 150 centimeters and 140 centimeters. 150 centimeters for the first x vector, first position vector, and 140 centimeters for the resultant vector. So I just put that in terms of meters, and I'm multiplying that. And now if you can see how this set it up, I'm just multiplying the hypotenuse by the trigonometric ratios. So I do that, and I multiply it just, normally, and I get this as my answer for the first position vector. Same thing, same rules here with the resultant vector. Now I just put it in terms of meters, 1.4, multiply it out. These are the two vectors I get. Now, since we know that this is the resultant vector, r, we know that it's caused by x1, x2. x1 plus x2. And if we look at this triangle, that's exactly what's happening. X1 plus x2 results in r. So if we do a little bit of algebraic manipulation, we get x2 is equal to r minus x1. We can substitute the vectors that we just solved for here, and vector subtraction is pretty much the same thing as normal subtraction, the x's are subtracted and the y's are subtracted. So if you do that, that results in this vector for the second position vector. Now we want to figure out the magnitude for this, and the way we do that is, again, you have, just never mind that. You just take the square root of the x component squared plus the y component squared. And with that, you get this answer 1.96 meters. Now this part I'm going to explain right now. Remember theta? Here it is. So this is the angle at which x2 is occurring. So if you notice, it's below the x-axis, so we're probably going to get a negative angle here. Let's take a look. So according to this, tangent theta is equal to the y component divided by the x component. And if we think about it, that makes sense. Imagine this is a triangle, y component over x component. Yeah, makes sense? Cool. So tangent theta equals y over x. If we isolate this, theta equals arctangent of the substitution of the y component and the x component of x2. And if you remember, it's right here. Just a little reminder. And when you substitute and solve, you get negative 15 degrees, which clockwise, in a clockwise fashion, is 345 degrees. So x2 is approximately 9.96 meters at 345 degrees.